Okay, so welcome back to this next video in which we are discussing quotient groups. Okay, so we're currently in the process of constructing the quotient group of G by N. Okay, and in the previous video what we did is we defined a composition law on this set of cosets of the normal subgroup capital N. Okay, and the way that we defined composition is that if we have two arbitrary cosets here, A bar and B bar, and we want to compose them together, so we want to know what is the answer to A bar composed with B bar, then the way we're going to define this is take a representative from each of these two cosets. So take a representative from A bar, okay, and we might as well take little a, the representative after which the entire coset has been named, okay. Take a representative from B bar, and again we might as well take little b. Okay, so you've got these two elements, little a and little b, from the original group capital G. And now what you're going to do is you're going to compose those two elements together with the composition of the original group capital G. So you compose A and B together in the original group. You can certainly do that. You'll get some answer in the original group, which we'll call A composed with B. Okay, and then the answer, quite simply, to what A bar composed with B bar is going to be equal to is the coset that contains A composed with B, basically. So A composed with B bar. Okay, and what we showed in the previous video is that, amazingly, if the subgroup that you're using here is a normal subgroup, then it turns out that this is well defined. Okay, because a big problem that you might be able to spot here is there are loads of different choices of representatives of these two cosets, A bar and B bar. Okay, what if you pick different representatives? You might end up with a different answer then. Okay, so what we showed in the previous video is that that's not the case, providing the subgroup we're using is a normal subgroup. Okay, providing the subgroup that you're using is a normal subgroup, you can pick any representative from this coset A bar, any representative from the coset B bar, compose the two of them together, and you'll always get an answer that's in the same coset. Of course, you might not necessarily get the same representative of this coset here, okay, but you'll end up with some representative of the same coset, so you'll always end up in the same coset, basically. Okay, right, so we have now proven that this does define one and only one composition table. Anyone could now use this to construct the same composition table. Everyone will get the same answer. Okay, so we have now defined a composition law on our quotient group to be, basically. What we now need to prove is that this composition law that I have just defined is a group composition law. I need to prove that this composition table here obeys the axioms of group theory. Okay, so let's now go through the axioms of group theory and discuss why this composition law is going to obey each of them. Okay, so axiom number 1 then of group theory, the composition law needs to be closed. Okay, so it needs to obey the closure property. Okay, so what does that mean? That means that when I compose any two elements of the group together, I must end up with another element of the group. Okay, so here are my elements of the group. So what I want to make sure of is that when you compose any two cosets together, you actually get another coset. Well, hopefully that's intuitively obvious by the way that this is actually defined. If you take any two arbitrary cosets in my quotient group to be here, and compose them together, you will always get another coset, because that's the very definition of this. Okay, remember what you do is you just take two representatives from each of those cosets, combine them together. Because the original group capital G is a group, you'll always end up with another element in the group, and then you just take the coset corresponding to that. So clearly, providing our original group is a group, then you will have a closed composition law here, basically. Okay, so whenever you compose two cosets together, you will end up with another coset. So this composition table is going to be closed. So that's a nice, easy one. Okay, now let's go on to axiom number 2, which is going to be slightly more difficult, okay, but not too difficult. So the next one we want to show is associativity. Okay, so what does this mean? Well, associativity means that if we want to compose three things together, so if we want to compose three cosets together, it should not matter where we actually put the brackets. So let's consider composing three cosets together. So let's consider A bar, and I'm sorry, the bar isn't particularly visible there, A bar composed with B bar composed with C bar. So we're now considering the composition of three cosets together, okay? And we want to show that it does not matter where you put the brackets. So we want to prove that you can either put the brackets here around A bar composed with B bar, so that means do the composition of A bar with B bar first and then compose the answer with C bar, or you can put the brackets around B bar composed with C bar, and we want to show that the answer is the same thing. So this is what we want to show, okay, that if you put the brackets around B bar composed with C bar like so, which now means firstly compose B bar with C bar with our composition law, okay, and then take A bar and compose it with the answer to B bar composed with C bar, okay, we want to show that whatever the answer to that is, it's the same as the answer here, and that that's true for all A bar, B bar, and C bar that you can pick, basically. Okay, so how are we going to show this? Well, quite simply, we're going to go back to our definition of composition and think about it. So we'll start off with the left-hand side here, we'll then go to the right-hand side, and then we'll see how it's always going to work out that these two are going to be equal to each other. Okay, so let's think about the left-hand side here. So if we're going to compose A bar with B bar, what is that actually equal to? Well, just by definition, we know exactly what that's equal to. That's going to be little a composed with little b, where this composition is composition in our original group. And you know what? I think I might actually color code compositions. So all of these composition symbols here, which I'm now coloring in blue, these mean the compositions in our quotient group. Okay? And now I'm going to colour this composition in orange, and this means composition in the old original group, capital G. Okay, so you compose little a with little b, which are our two chosen representatives from these cosets A bar and B bar. They're the most obvious ones to use, but of course we've shown that you could use whichever one you like, but we might as well use those two. And then we'll take the coset that contains A composed with B. Okay, so that's the answer to A bar composed with B bar here. And now we're going to take that answer, that coset, and we're then going to compose it with C bar here. Okay, and this composition now is composition in our quotient group, so I'll colour that in blue. Okay, so that was just using the definition, and now I can go further. I can use the definition again. So now I want to compose this coset with this coset. How do I do that? Well, I just take a representative from this coset and compose it with a representative from this coset in the old group composition law, and then I take the coset that contains that representative. Okay, so quite simply, let's take the representative A composed with B. Why would we not take that representative? We can choose whichever representative we like to perform this composition, so the most obvious one to use is A composed with B. We will compose it with little c, again the most obvious representative to use from C bar, okay, and all of these compositions now are in our original group, so I'll colour them in orange, and then quite simply we'll take the coset that contains that element, A composed with B composed with C. Okay, and that's as far as I want to go with that, so this basically is equal to this. Okay, so that's the left-hand side. Now let's do the right-hand side. Let's have a look at what the right-hand side is going to be equal to, and then we'll see that the right-hand side will always equal the left-hand side. Okay, right, so once again, let's firstly do B bar composed with C bar. So hopefully you're getting used to this now. So first I'll just put in the A bar and composed, and that's still composition in the quotient group. But now we can replace B bar composed with C bar with B composed with C in the original group, so I will colour in that composition in orange there, and then we'll take the coset that contains B composed with C. Okay, so there we go, that's slight progress. And now we'll again get rid of this composition and replace it again with a composition of the group. So if we want to compose A bar with the coset containing B composed with C, B composed with C bar, then again we need a representative from here, and we're just composing it in the original group with our representative from here. And of course the two representatives that we'll use are A from A bar, and then we'll have B composed with C from B composed with C bar. Okay, so now all of these compositions here are in our original group, and then quite simply we'll take the coset that contains that element, and that now is our developed right hand side basically. Okay, now why is it the case that this coset is always equal to this coset? Well, quite simply the reason that this coset is always equal to this coset is because the element A composed with B composed with C, okay, in the group, in our original group, capital G, okay, so this element here that we are taking the coset that contains it is exactly equal to the element A composed with, B composed with C, okay, because the original group is a group and therefore obeys associativity, and all of this is just composition in our original group, so these two elements must be exactly the same. So the answer to this left hand side is the coset containing this element, the answer to the right hand side is the coset containing this element. Those two elements are exactly the same thing, therefore these two cosets must be exactly the same thing. Hence, what we have shown is that this must be true, basically. Okay, so composition of the cosets in our quotient group, according to the composition law that I've just defined for you, does obey associativity, basically. Okay, right, so that's axiom number 2 of group theory shown. Okay, next up we want to prove axiom number 3. Okay, so we want to show that there is an identity element. We want to show that there is some element in our quotient group which will compose on the left or on the right with any other element to give back that arbitrary other element back again. Okay, so we want to show that there is an identity element. Now, the identity element then, what is going to be our identity element in our quotient group? Well, the identity element is actually going to be the normal subgroup itself. Now, why is the normal subgroup going to be the identity element here? Well, because the normal subgroup will always contain the identity element of the original group. Okay, so another way that we can call the normal subgroup is we can call it E bar, basically, the coset of the normal subgroup that contains the identity element, which of course is the normal subgroup itself. Okay, right, so my claim then is that E bar, this coset containing the identity element of the original group, is going to be our identity in the quotient group, basically. Okay, now how can I show this? Well, what I need to show is that if I take any arbitrary element from my quotient group, so let's say A bar, and I multiply it on the left with this coset containing the identity E bar here, that I will end up with A bar back again. So that's one of the things I need to show, and I need to show that for all possible cosets. So if I show it for a general coset A bar, then I will have shown that. Okay. And I also need to show that it works the same if you multiply on the right by E bar. So again, an arbitrary coset A bar composed with E bar on the right this time is again going to equal A bar. So these are the things that I need to show. Okay, and hopefully again this should be pretty obvious. Okay, so all I'm going to do to show this is just use my composition law, and again I'll just color code this in. So I'll color this composition here in blue because that means composition in my quotient group, composition of the cosets. Okay, right, so let's just use the definition that I have given you for composition of the cosets in the quotient group. So if I want to compose the coset containing E with the coset containing A, how do I do it? I need a representative from here and a representative from here. What's the most obvious representatives to use? Well, of course, it's just E, the identity of the original group, and A. And I'm sorry, I wrote A there. That should be the composition. I'll color code it in to hide my mistake. So that's our composition now in the original group. So I just compose the identity, my representative of E bar, with A, my representative of A bar, and I take the coset that contains that. Okay, now of course the identity in the original group will compose with A to give A back again, so this is just the coset containing A. Okay, and that's exactly what I wanted to show. Okay, so that's the top one done, and the bottom one can be done in exactly the same way. Okay, so I'll just spell it out again. It'll just reaffirm the argument for you. Okay, so if I want to compose these two things together, again I take a representative from here, a representative from here, I'll take A and E, and I compose them together in the original group, capital G, so this is composition in my original group, so I've coloured it in orange, and I take the coset that contains this answer, basically, A composed with E, but of course A composed with E is just equal to A, so the answer here just becomes A bar, the coset containing A. Okay, so that also shows me that. And that was truly general. I didn't say anything about little a. It could have been any element of the group, the original group, which means that this coset, A bar, could have been any of the cosets within the quotient group, so this works for all of them, basically. Okay, so we do have an identity element, which is just our normal subgroup. Okay, the coset that contains the identity element, basically, of the original group. Okay, so that proves that we have an identity element in our composition law, and finally, what we want to prove is that we have inverses. So we want to prove that for any coset in the quotient group, you have another coset which will compose with it either way around to give the identity element. Okay, so we want to show now that our composition law has inverses, basically. Okay, so we want to show then that for all, let's say, A bar, which is an element of our quotient group, G over N, we want to show that there exists another coset, okay, which we'll call A bar inverse, such that, okay, and that needs to be an element of the quotient group as well. I've missed that bit out, I'll just stick that in, so which is an element of G over N, such that A bar composed in the quotient group with A bar's inverse is equal to the identity element, which is E bar, and also A bar inverse composed in the quotient group with A bar is also equal to the identity element, which is E bar. Okay, right. So this needs to be true for all little A bar in this quotient group G over N, basically. Okay, right. So how are we going to show this then? Okay. Well, we need to find A bar inverse, basically. We need to take an arbitrary element of the quotient group and show that we do in fact have an inverse for it. Okay, so have a little think about this. How can we do this? Okay, well, it helps to remember how I have defined composition here. Remember, you pick representatives from the cosets and compose those two together. Now, if we think about A bar, what is the most natural representative to use? Well, it is the element little a, basically. We always use the element little a. Okay, so what could we compose with little a that would give us an element of the identity coset? Okay, well, we could compose it with A inverse. Okay, and that will give us the identity element in the original group. Okay, so here, this composition is the composition of our original group. So because our original group is indeed a group, the element little a will have an inverse in the original group. Okay, so those two will compose either way around to give the identity element. So I could also have it this way around. A inverse composed with A is equal to the identity as well. Okay, so why don't I just use the coset that contains A inverse? Okay, so if I found the coset that contains A inverse, if I found A inverse bar, okay, then wouldn't this coset compose in my quotient group with A bar to give the identity coset E bar? Okay, and the answer is yes, so let's just go through exactly why that is. So if I now consider what is A bar composed with the coset that contains A inverse, so A inverse bar, okay, and this composition here means composition in the quotient group, okay, then what's it going to be equal to? Well, quite simply, I'll take a representative from each of these cosets, and of course I'll use A and A inverse, okay, and I'll compose those two together in the original group, which will give me the identity element, and then I'll take the coset that contains the identity element, which is, of course, E bar. Okay, so there I have found the coset that satisfies the top one, okay, and it will also satisfy the bottom one, quite simply because if I do it the other way around, so if I take A inverse bar, the coset containing A inverse, and I compose it with A bar, the coset containing A, the other way round, then once again the way I'll do this is I'll just take a representative from both, and I will pick the representative A inverse and A, okay, compose those two together in the original group to get the identity back again, so again this will just equal E bar. Okay, so if you want to know what is the inverse element within the quotient group of a coset A bar, quite simply find the coset that contains the inverse element for little a, basically. Okay, find the coset containing A inverse. Now note, it might be the case that A inverse is actually in the same coset as A. Okay, if they're in the same coset as each other, then of course that coset will be its own inverse, is what that means, basically. Okay, so if A and A inverse happen to be in the same coset, then the coset in the quotient group will be its own inverse. You do not need to worry about the composition law not being well defined, because we've proven that it is well defined. Okay, so let's imagine that that was the case. So if A and A inverse were in the same coset, and we wanted to then compose A bar with itself, okay, and I wanted to show that this is equal to the identity coset, then again, how would I do this? I'd pick a representative from A bar, but I don't have to pick the same representative twice. So I could pick the representative A for this one, and then pick the representative A inverse for this one. So I've assumed now that A inverse was an element of the same coset as A, okay, so quite simply I've picked two representatives from A, and I'm composing the two of them together in the original group. So here is composition in the original group, and that will give me the identity element. Okay, so the answer here must be E bar, basically. Okay, so you do not need to worry about the scenario that A inverse ends up being in the same coset as A. All that means is that the coset is its own inverse, and the way of seeing that is when you have A bar composed with A bar, you could pick A for the representative for the first one, and then A inverse as the representative for the second one. We've already proven that it does not matter which representatives you pick. The composition law is well defined, so that means that this must be E bar. Okay, it must be equal to the coset containing the identity element. Okay, right, so that now proves then that this composition law that I have defined on this set of cosets actually does obey the axioms of group theory. So now we have completed the construction of a quotient group. That is what you do. You take a normal subgroup, you partition the group up into the cosets of that normal subgroup, and then the elements of your quotient group, G over N, are going to be these cosets, basically, or equivalence classes of the normal subgroup. And the way that you define composition of those, of any two cosets in that quotient group together is just by taking representatives from the cosets, combining the two of them together in the original composition law on the original group, G, okay, and then taking as your answer the coset that contains the answer to the two representatives composed together in the original group. Okay, and we've now proven that that does obey the axioms of group theory. So that is what a quotient group basically is. In the next video, what we'll do is we'll have a look at an example of doing this.